Hello dear students of plus one medical, non-medical and respected teachers. In this video I am going to discuss oscillations of a mass attached to a spring when it is held horizontal and when it is held vertical. And I am going to prove that the oscillations of the mass will be simple harmonic in nature, and we have to derive expression for time period of oscillations of the mass attached to the spring. So let us start with open mind. First of all, suppose when spring is held horizontal. Suppose this is rigid support A and a spring or spring constant K, AB, and to the free end B, a mass M is attached so that it is in equilibrium, that is, this is the equilibrium state of the mass and spring. Now, when this mass M is pulled towards right through a small displacement x, then a restoring force comes into play, which tends to bring the mass back to the equilibrium position. By Hooke's law, this restoring force is equal to minus kx, where k is the spring constant or spring factor, which depends upon the nature of the material of the spring. So, restoring force by Hooke's law is given by F is equal to minus kx. Suppose this is equation number 1. Now, when this mass m is released after pulling it through a distance x, then it turns back to the equilibrium position or mean position due to this force, restoring force due to Hooke's law. As a result, it gains speed, gains kinetic energy, and overshoots the mean position, and the spring gets compressed. When it overshoots the mean position, it restoring force again comes into play, which opposes the motion of the mass, and it stops after covering a distance x from the mean position, that is, after attaining left extreme position, and then it turns back. So this process continues. This mass m starts oscillating about its mean position on a frictionless surface, and these oscillations are simple harmonic in nature that we are going to prove. So this to and fro motion and the oscillations of mass due to compression and extension of spring are simple harmonic in nature. To prove it, since F is equal to minus kx in accordance with the Hooke's law, and by Newton's second law of motion, F is equal to ma, where a is the acceleration produced in the mass. So comparing 1 and 2, so we have ma is equal to minus kx, or a is equal to minus k by m into x. As k by m is constant, so a is directly proportional to minus x. It means acceleration of the mass m is directly proportional to its displacement from the mean position, and negative sign shows that it is directed toward the mean position. So oscillations of the mass are simple harmonic in nature. If the oscillations are simple harmonic in nature, then if t is equal to time period, t must be equal to 2 pi under root displacement over acceleration, that we have already derived, or t is equal to 2 pi under root x upon a square root. Okay, because a is acceleration and x is the displacement from the mean position. So also using the value of a from this equation, so we have t is equal to 2 pi under root x upon k by m into x. So x cancels, so t is equal to 2 pi under root m upon k, which is the required expression for time period of oscillation of a mass attached to a spring of spring constant k held or kept horizontal, so that it oscillates freely on a frictionless surface about its mean position. So where m is called mass, or it is also called inertia factor, and k is called spring factor or force constant, which is defined as force per unit extension produced, which depends upon nature of the spring. So T is equal to 2 pi under root m upon K. Now, when spring is held vertical, suppose this is the spring. So capital L is the original length of the spring, or suppose a mass m is attached to its free end, so that spring gets extended through L, where L is the extension produced in the spring and mass is in equilibrium. What is force acting? Weight mg and F1 acting upward due to elasticity of the spring. Now, when this mass is further pulled down through a displacement x, then again weight is acting vertically downward, but upward force which is taking back to its mean position is F2. Now, by Hooke's law, in equilibrium in the second figure, F1 must be equal to storing force must be equal to minus KL by Hooke's law. F1 is equal to minus KL. Also, weight is acting vertically downward. So in equilibrium, this F1 must be equal to mg. That is, mg is equal to KL numerically, or K is equal to mg upon L. This implies K is directly proportional to 1 by L, where L is the extension produced. This gives the expression for K. It means more is the length of the spring, less is the spring constant. If length of spring is doubled, so spring constant will be half. If it is made half, it becomes twice. So then after extending it or pulling it through small displacement x, F2 is given by, now total extension produces L plus x. So F2 must be equal to minus K into L plus x by Hooke's law. Equation number 6. Therefore, net upward force which takes the mass m back to the mean position after it was pulled through distance x is given by F2 minus F1. This is the net force acting in the upward direction after pulling the mass m down through displacement x. L is the extension produced when mass m was attached to the spring at the bottom. So F2 minus F1 is equal to minus K into L plus x minus KL. So simplifying minus KL minus KX plus KL. KL cancels, so F is equal to minus KX. Again F is equal to MA, or MA is equal to minus KX, or A is equal to minus K upon M into X, or A is directly proportional to minus X, or K by M is constant. It means oscillations of mass M attached to the free end of the spring kept horizontal, and when it is pulled are simple harmonic in nature. If they are simple harmonic in nature, if T is the time period 2 pi under root displacement of acceleration, or 2 pi under root x upon K by M into X, x cancels. Again we have T is equal to 2 pi under root M by K. In both the cases, whether the mass M is held horizontal or mass M or spring is kept vertical, then time period of oscillation of the mass M attached to the spring is T is equal to 2 pi under root M by K in both the cases. Maybe such the value of K, which is mg upon L. So it comes out to be T 2 pi under root M upon mg upon L. Cancels. So T is equal to 2 pi under root L upon G. So time period of a loaded massless spring held vertical or horizontal, is given by T is equal to 2 pi under root L upon G. Now it is similar expression for time period of simple pendulum, but only difference is in this case L is the extension produced in the spring when mass is attached, but in case of simple pendulum L is the length of simple pendulum, that is distance between point of suspension and point of oscillation. So this is the difference, but formula is exactly similar. So which is the required expression for time period of mass attached to a spring, whether it is held horizontal or it is held vertical. So from this we see that mass M or K spring constant, they are related to each other. K is equal to mg by L. Suppose we have two springs, or spring is cut, spring of length is cut in two equal halves. Question may be asked, then what will be the spring constant of each half? Now, when spring is cut into two halves, length becomes half and K is inversely proportional to L. Therefore, new spring constant of each part will be 2K. So it means spring constant or spring factor depends upon the length of the spring. This is all about oscillations of a mass attached to spring. So good luck, be happy, all the best, stay tuned till next video. Sarbat da Palau.